Welcome to this concept explainer brought to you by CBSE ScoreLab of ProfSam.com. That is ProfSam.com. Today, we're starting a deep dive into a really core idea from Unit 2 electrostatic potential and capacitance. We'll be focusing on the potential due to a single point charge. Our goal is simple: to explain this V equals KQ by R formula so clearly that you lose any fear of the maths and, remember it securely for your exams. So let's start with a simple question. Imagine you rub a balloon, give it a bit of static charge, like a tiny point charge. Now, if you take this balloon, say, 10 meters away from a point P, does that spot P still feel the influence of the charge?
Yes, it must feel some influence, but very weakly, right? Like the electric field decreases really quickly.
Exactly. That influence is what we call potential. Now, here's the surprising, or maybe the counterintuitive fact. The electric field, E, created by that point charge, it drops off very fast, as 1 by r squared. But the potential, V, it only drops off as 1 by r. This means potential is, while it's more persistent, it reaches further than the electric field.
Okay.
We really need to understand why this difference in r is so important.
Wow. Okay, so if I'm sitting far away from a charge, the electric field is tiny, but the potential is comparatively huge. That is definitely counterintuitive.
It is, isn't it? And that's where the power of this concept lies. Okay, let's unpack this. The core idea here is that a single isolated charge creates an electrical landscape around it. Think of it like a steep hill if the charge is positive, or a deep funnel if it's negative. Our goal is just to map the height of this landscape at every single point.
So potential is like the height of the electrical hill. But why do we even need this concept? Why not just use the potential energy?
Good question. Very good question. See, potential energy, U, it depends on the size of the test charge, Q, that you move. If you move a 2 Coulomb charge, you get twice the energy of moving a 1 Coulomb charge. We want a standardized map, one that describes the location itself, independent of whatever charge we place there. This is why potential, V, exists. It's simply energy per unit charge. So V equals U by Q.
I see. So dividing by the test charge Q standardizes the map. It removes the dependency on the size of that test charge.
Absolutely, that's the whole point. And for a mental picture, just imagine a glowing sphere. That's our source charge Q. And it's surrounded by these concentric, transparent, spherical shells. The shell closest to Q is high potential. Let's say it's bright red, and then the potential just fades smoothly to black, which is zero potential, far away. This visual shows that potential is spherically symmetric for a point charge.
That mental image makes sense. All points on the same shell have the same height or potential.
Now, let's see how insert defines this and formalizes the mathematics. Could you read the definition for the electrostatic potential V of R due to a point charge Q?
Yes. It says potential at a point with position vector r due to a point charge q placed at the origin is given by V of r is equal to 1 upon 4 pi epsilon naught q by r. The formula is simple, but why is it 1 by r? Remember, electric field was 1 by r squared. How do we go from 1 by r squared to 1 by r?
That is the key insight. That's the most important question. Potential is derived from the electric field through integration. We can follow a simple four-step concept build. Step 1, we start with the electric field formula. E equals KQ by r squared. This is the force per unit charge. Step 2, work done, W. To move a charge against this force is basically force times distance, or more correctly, the integral of the field, E over the distance, Dr.
Wait. When we do this, we are bringing the charge from infinity, right? Why from infinity?
Yeah.
Yes, good point. We use infinity as our reference, our 0 point. Think of it as the ground level. We assume potential is 0 there, and we measure the height of our electrical hill relative to that ground level. So, step 3, when you integrate the function 1 by r squared, mathematically you get 1 by r. The power just increases by 1, from -2 to -1. And therefore, step 4, the result for potential, V, is proportional to 1 by r. We lose 1 power of r because we calculated energy over a distance. Hope everything is clear so far. This concept explainer is from ProfSam.com. That is ProfSam.com. Now let's try a very simple worked example. If we have a charge, Q equals 4 into 10 to the power of -7 coulombs, and it's located 9 centimeters, or 0.09 meters away from a point P. What is the potential V at P? Just remember, the value of 1 by 4 pi epsilon naught is 9 into 10 to the power of 9. Okay, so V is equal to 9 into 10 to the power of 9 times 4 into 10 to the power of -7, all divided by 0.09.
Correct. And the math simplifies quite nicely. You see, 4 divided by 0.09 is about 44.4, which results in a potential of 4 into 10 to the power of 4 volts. A massive positive scalar value, you see. And if we connect this to the bigger picture, calculating potential, a scalar, by integrating the electric field, which is a vector. This is the conceptual bridge in physics. This idea of voltage that we derive today, it's the fundamental starting point for all of Unit 3 current electricity. Now let's tackle 2 exam-killing misconceptions, the silent killers. The first one is just formula confusion. Students so often assume V must be proportional to 1 by R squared, just like Coulomb's law.
Right, because we spend so much time on that in Unit 1.
Exactly. So the wrong idea is V equals KQ by R squared. Students think it because of habit. The correct idea is, of course, V equals KQ by R. And the remember hook, we integrate E over a distance to get V, so you lose a power of R. The second silent killer is the sign convention. Potential is a scalar, but unlike gravitational potential, it can be negative.
So if the source charge is negative, the potential is also negative. This means electric potential is like money. It can be positive or negative, but it has no direction.
That is a perfect way to think about it. The wrong idea is that potential must always be positive. Students think this because they confuse it with magnitude or the work you have to do, which is usually positive. The correct idea is that potential is a scalar quantity, and it always carries the sign of the source charge Q. So plus Q creates a plus V, a hill, and minus Q creates a minus V, a valley. Now, to lock this concept in your memory, let's use 2 anchors. For the formula, use this mnemonic. V has 1 leg, E has 2 legs, R squared. Simple, no.
V has 1 leg, E has 2 legs. Okay, I can remember that.
The catchy phrase we must remember is, potential is persistent. It falls slower. And finally, let's use that physical gesture. Just lift a pen high. That's high potential. The pen wants to drop, to go to low potential. That's the core idea. All right, to finish this deep dive, here are 3 exam-safe factual bullets summarizing everything. 1. Potential, V, due to a point charge Q, is proportional to 1 by R2. This potential is spherically symmetric around the charge. All points at the same distance R have the same potential. And 3, potential is a scalar quantity, which means we just add the numbers algebraically, always respecting the positive or negative sign of the charge. Remember, understanding potential is the key to mastering electrostatics. To get maximum marks in 12 CBSE physics, chemistry, and maths, visit ProfSam.com.
That is ProfSam, right?
Yes, ProfSam.com. Study well and keep practicing.